Shall I make a start then? So welcome everyone to, I think it's the first Breathing City seminar of the year. We've made an executive decision to skip the intro slides, which we show every time because we've probably all seen them before. So my name is Alison Tomlin and I'm chairing talk from Chris Iddon today. So we're very pleased to have Chris with us. Chris is a ventilation expert and currently a visiting researcher at University College London. And he has worked historically on assessing the role of the built environment on the risk of COVID transmission and ventilation strategies more generally. He's currently the vice chair of the Natural Ventilation Group at the Chartered Institution of Building Services Engineers, and he co-authored a couple of their guidance documents on COVID ventilation and air cleaning tech. So today, Chris is going to talk about one of my favourite topics, which is partly about uncertainty analysis of models and how that can be combined with experimental data in the design of effective ventilation strategies. So we're very pleased to have you, Chris, and very much looking forward to your talk.
Thank you very much, Alison. Just hoping that that's coming through now. Share the screen.
I'll switch myself off.
Move this bar. Yes. Okay. Is that coming through okay, Alison?
Yeah, all looks good. I can see the
Great.
slides and your pointer. Yeah.
And I'll just set my timer going so I know how long I've been waffling on for. Okay, so thank you very much for inviting me, and today I'm going to talk about uncertainties in airborne COVID-19 transmission, why they matter when considering ventilation to reduce risk. As all great scientists, we stand on the shoulder of giants. I was part of the AirBOD team, which was the Airborne Infection Reduction through Building Operation and Design for SARS-CoV-2, and there were many people whom I've had lots of interactions with and discussions and writing papers with, and without the help and the aid of all these people, the thought processes I'm going to be sharing today wouldn't be possible. So I just wanted to thank all those. Right, so a quick overview. I'm going to be looking at the uncertainty in mass balance models, and then the uncertainty in viral emission rates, and finally discussing exposed and susceptible populations and the application of these kind of models to case studies. It'd be useful to have questions at the end, or you can put them in the chat box, but I'll probably take them at the end. And the reason being is that I'm going to be running several different threads that are going to be intertwined in a kind of Christopher Columbus style film. And it might be that you'll have a question and I'll maybe answer it, or hopefully I'll answer it as a talk progresses. So mass balance model, and this is what we've been using. It's a fairly simple model. And we make some simple assumptions to help us do some simple mathematics. So in essence, we can imagine we have an infector who's emitting some viruses that are encapsulated within aerosols or respiratory particles of a variety of different sizes. But what we're particularly interested in is the amount of virus that is being emitted into the space. And the virus emitted into the space can also be removed from the space. And there are several mechanisms that can be used to remove. Ventilation can be by exchanging the air with the outside, or through filtration, whether in-room filtration or through HVAC filtration. These aerosol or respiratory particles can become deposited on surfaces, and the virus itself will decay over time. So there are a number of different removal mechanisms we can consider, and we can build a fairly simple model where we take the gains, which is the emissions from a person, and the losses. And all these various different losses that I've described are additive, and we have a final removal value we call phi. And that enables us to estimate the steady state of the number of viruses within a space, just by knowing the emission rate and also dividing it by the removal rate, which is in air changes. And then we can then estimate the concentration of the virus in the air. I'm going to just be considering 3 different office type spaces to begin with: a 20-person, a 5-person, and a 50-person office. And what I'm doing is I'm preserving the space volume per person. So I'm giving them 10 square meters per person And I'm assuming that we've got a floor to ceiling height of 3 meters, gives us 30 square meters. And I'm giving them 10 liters per second per person of ventilation. So what you can see here is that we've got more ventilation in terms of liters per second in the 50-person office, but the air change rate is exactly the same because we've preserved the per person space volume. So imagine we had a hermetically sealed 20-person office and we added an infector who's emitting viruses at 1,000 viruses per hour. What would happen is that the number of viruses would increase linearly over time, adding an extra 1,000 viruses per hour. So we'd get to a point after an 8-hour day that there'd be 8,000 viruses in the office. Now, of course, that doesn't happen because there are removal mechanisms. So let's consider ventilation as our first removal mechanism. I mentioned 20-person office, so adding 200 liters per second, that's over 700 meter cube per hour. So every hour we're adding 1,000 viruses, and every hour we're removing over 700 meter cubed of air from within the space and replenishing it with outside air that has no virus. So what you see is that over time we reach a steady state. And this steady state in this example, if you're emitting 1,000 viruses, would be just over 830 viruses within the entire volume of the room. So our mass balance model also considered other removal mechanisms, biological decay and deposition. So I'm going to use a couple of values for that, and we add them all together. So now our total removal for the office is 2.25 air changes per hour. And with just the ventilation, a steady state was 830, but once we consider those other removal mechanisms, steady state drops to about 440 viruses in the room. But we're not really interested in how many viruses are in the room. What we're interested in is the concentration of the viruses in the room. So we divide that value by the room volume, and the room volume is 600 meter cube, and now we have a steady state of just less than one virus or virions per meter cubed of air. Doesn't seem like an awful lot. Let's just go and consider 5, 20 and 50-person offices. If we look at the steady state number of viruses in the air, they're all exactly the same, as the steady state is directly proportional to the removal mechanisms in air changes, but the concentration is proportional to the removal rate in equivalent airflow. So in terms of equivalent liters per second of clean air. And we can see here, here's our 20-person office. And the 50-person office, even though it's got exactly the same number of viruses, the concentration is less because the room volume of our 50-person office is so much greater. And our 5-person office, being of a smaller volume, there's a much greater concentration of virus in the air. In fact, there's a 10-fold difference between the 50-person and the 5-person office. So what can we do with ventilation? Well, ventilation enables us to reduce the concentration of the virus even further. But you can see here, as we add an extra 10 liters per second of ventilation air, that the more ventilation air that we provide, the amount of the concentration reduces at a slower rate. But this is because the concentration is inversely proportional to ventilation. So there was a law of diminishing returns. For every extra bit of ventilation we add, we have a lower effect on reducing the concentration in the air. We can have the same effect by increasing the space volume. So we can maintain the same ventilation rate, but we can increase the space volume because the removal mechanisms are linked to the space volume in air changes. We also see this law of diminishing return. So we've now got a picture using these models of the concentration of virus in the air, but what we're interested in is how much virus someone who's susceptible is inhaling. If they are sharing that space with someone exhaling 1,000 viruses per hour. So we have to consider a few things. So the amount, what we have to consider is the breathing rate of the person in the room. So how much of this air they are inhaling over time. And then we also have to consider the likelihood of the virus becoming embedded within the respiratory tract. Because what we know is that if you inhale very fine particulates and then exhale, you're going to exhale most of them back out again. They don't all become embedded within the respiratory tract, so we have a deposition feature. I'm just going to use a couple of values here from the literature, and we can see that over time our dose increases almost linearly. You have this little hockey stick effect right at the beginning where the concentration of the virus is building up times 0. And essentially we get this kind of proportional effect that the inhaled dose is proportional to the concentration of the virus in the air. We look back again at the 5 and 50 person office, compare it to the 20 person office. You can see because there is a 10-fold increase in the concentration in the 5 person office, you get a 10-fold increase in the dose. So that would mean from an individual perspective, if I'm sharing the 5 person office with someone exhaling 1,000 viruses per hour, I'm going to be inhaling 10 times more than I would if I was sharing the same space, the same infector in a 50 person office. And this is interesting to note because it enables us to consider a relative risk, which is where we can consider the inhaled dose in a comparator scenario with a reference scenario. So we can compare a, say, 50 person space with a 5 person space, or we can consider a 20 person space ventilated at 5 litres per second with a 20 person space ventilated at 10 litres per second per person. And this gives us a kind of an indication of what the relative risk would be if we were to share those same spaces with the same infector having the same emission profile. We use this relative risk because we really don't know what the emission rate is of the infector we're sharing a space. And we really don't know what the dose response is going to be. So using a relative risk enables us to cancel out these unknowns, still enable us to have an estimate of the relative riskiness of the space. However, it has some drawbacks. What if I'm sharing it with no infectors? So there would be a relative risk difference, but the absolute risk would still be 0. Anyway, I said I was going to talk about uncertainty, and so far I haven't. I've just been using some values just to give you a flavour for how this model works and the kind of values that we're interested in when we're trying to determine what the inhaled dose is. So I'm going to consider some uncertainty in some of the general inputs, and these are taken from the literature. So biological decay has a distribution. So we use a log normal distribution, and these are in air change rates. This biological decay is the decay of the virus over time if it is suspended in an aerosol, suspended in air in the dark. And that's where these values are taken from. So I'm not considering the very rapid decay of pathogens that we know occurs at the initial release of viruses encapsulated in respiratory particles, because when they're initially released, they come from a very high humid space within our respiratory tract, and they evaporate very, very rapidly, and that causes chemical changes within the fluids encapsulated within the aerosols that can render the virus or pathogen inviable quite quickly. And there's some really interesting work coming out of a group in Bristol at the moment looking at that. So I'm just going to say for this model, we're going to assume that that doesn't occur, just to simplify our model. And it just gives us a conservative effect, because what we're essentially saying is we don't anticipate that the viruses that we predict to be being emitted by the person, a good proportion of those are becoming instantly unviable. So we're just ignoring that at the moment. And surface deposition, there's some values to estimate the deposition of small particulates in the same size range of the aerosols that we're considering, and respiratory tract absorption factor. But we also can take some values from the literature taken from studies that look at delivery of drugs in aerosol form, particularly like asthma drugs and so forth. And breathing rates, there are good literature studies on the breathing rates of adults at rest or walking or running and these kind of things. So here I'm using breathing rates from an adult at rest Saturday. So when we apply those uncertainties, we can now see that instead of a single value for steady state concentration, we have a range of values. So shown here the 95% confidence intervals for the concentration of the virus within the space. And that's then going to have an effect on the dose. So we have a range of uncertainty now. So for the same assumption of somebody emitting 1,000 viruses per hour, we now have an uncertainty of the inhaled dose being somewhere between 0.94 and 2.86 viruses over 8 hours. We can use ventilation and just have a look at the effect of ventilation for this 20-person office and someone emitting 1,000 viruses per hour. And we can see here that we get this law of diminishing returns and the effect of adding ventilation to an unventilated space, adding 200 litres here, so that's 10 litres per second per person, has a pretty decent effect at reducing the number of viruses that we are likely to inhale. But adding further ventilation, because there's quite a large overlap now between this uncertainty, although our median assumption is that we're going to see some reduction, that reduction in inhaled dose becomes quite small, and becomes blurred by these uncertainties, so it becomes more challenging to be confident that we're going to see a measurable effect. So the uncertainties that we're considering here are just these few. So imagine I did inhale 2 viruses. If I was sharing this 20-person office with someone emitting 1,000 viruses per hour, what is my probability of becoming infected? Well, I'm showing here a dose curve, and dose curve is described by this equation here where we have a dose constant, and the dose constant is the number of inhaled viruses that will give rise to a 63% chance of becoming infected. Now, I'm not going to go into too much detail here, but we've looked at the literature for the human challenge study, and we've assumed a uniform distribution of somewhere between, this dose constant being somewhere between 5 and 15 viruses. So if you inhale that amount of viruses, we're confident that that gives a 63% chance of becoming infected. So if you were to inhale 2 viruses, you have somewhere between, I don't know, maybe 15 to 30% chance of becoming infected. So a relatively high risk of being infected. What we have to remember is that not every virus that we inhale, even if it does deposit within our respiratory tract, is going to get over the mucosal membrane, get past the innate immune system, bind to the receptor, become engulfed into the cell, and then be able to start replicating and creating more viruses. So it doesn't always happen. So that's why we have these kind of dose responses. And these dose responses might vary from person to person. Okay, and now I'm going to move on to considering viral emission characteristics. If we consider an infected person, it becomes infected sometime before symptoms start. So this time here is when symptoms start, time 0. Once this virus gets hold and starts to replicate, it will then replicate, infect other neighboring cells, replicate even further until we get a huge rise in the number of viruses being produced by the host or the person who's become infected. So over time, we get this increase in the concentration of virus until hopefully our immune system kicks in and is able to defeat the virus or whatever the other pathogen is, and then we'll see the amount of virus within the infected decrease over time. So we have this temporal distribution of viral emission characteristics. However, there's also between person distributions. So one person's peak is going to be very different to another person's peak concentration of virus. And so to describe this, we take some data from a paper by Chen et al. In 2021, where they used a PCR test where they took the nasal pharyngeal swabs. I don't know if you probably remember back in the day when we used to do the swabs, so you the probe your nose and give it a little wipe around, and then dilute it into a little bit of buffer. And then that buffer is taken and undergoes RT-PCR to have a look at kind of semi-quantifying the amount of genomic material that is in there. So we're talking about viral genomic material here. And they did that with several hundred people and found this probability distribution. I'm interested in this pink line here. The purple line is those who had severe symptoms, and the pink line is those who didn't show severe symptoms. And this distribution can be described by a log distribution with a mean of 7 and a deviation of 1.4. So it's 10 to the power of 7 to give us this log distribution here. So this is the distribution plotted on this graph, and the cumulative distribution is this curve here. And you'll also see lots of these little red dots. These red dots are actual data. This is actual data from the ONS survey. And the ONS survey took a random sample of people who every week would provide a PCR swab of data. And for those that are positive, they provide the median, the 75, the 25, the 97.5, and the 2.5 percentile values for the kind of viral loading. And these differ from week to week. So I've just plotted them here on this graph, but it just enables us to see that our model that we're going to be using here as this cumulative distribution and actual data is slightly adjusted to the left. So if anything, this model assumption of the viral load of genomic material is slightly conservative in that it slightly overestimates the viral load of a range of people. So given a population of people who are infected, they're going to have a range of viral loads that differ over maybe 9 orders of magnitude. And this is massive. So this is a log scale here, and this is the uncertainty that is really huge, and we have to really consider this when we're talking about 9 orders of magnitude. That is like considering a pea, which has a diameter of about 1 centimeter, with the Earth, which has a diameter of about 10,000 kilometers. So these are the kind of orders of magnitude that we're describing here. It's absolutely huge. And of course, that makes a big impact on the predicted inhaled dose. So I was talking about someone emitting 1,000 viruses per hour in the person office example, but it really could range massively. Okay, so what is this genomic material? This is just showing how a coronavirus fuses with a cell, infects the cell, and then starts to replicate. So it replicates its genome many, many, many times. So I have loads of fragments of genome flying around within the cytoplasm of the cell. Some of these fragments are used to create the proteins that go on the surface of the coronavirus. And the idea is that the virus wants to package its nucleocapsid with the proteins to create new virions, which will then exocytose and go on to infect other cells. And this happens at a huge kind of industrial scale, but millions and millions of these are being formed. But not all of them will go on to form these nice viable virions, while a lot of this fragments of RNA will make its way into the respiratory fluid. So when we are talking about RT-PCR swabs and the genomic viral load, we're not necessarily talking about a viable virus. A lot of it is just fragments of RNA. And then also when we get an immune response and our body starts to attack these viruses and render them unviable, we also have more fragments of RNA that are not viable viruses. So let's have a look at some data from the human challenge study. And they took these nose and throat swabs and they measured the genomic material using RT-PCR. And they also were able to measure the viral load by culture. So this is actual virus that they could quantify or semi-quantify using a particular assay. And you can see that days after inoculation, the peak is getting into the order of 100 to 1,000 viable viruses per mil of swab material. And we can compare that to the genomic material, which is maybe 4 or 5 orders of magnitude greater. So although we can fairly easily measure this genomic material, what it will give us a clue is the distribution of the viral material, the actual viable virus. But the viable virus is going to be orders of magnitude smaller in terms of the number of viable viruses to the genomic material. And we assume in our model that it's between 100 genomic copies to 10,000 genomic copies are required to relate to one viable virus. And that enables us to generate these kind of emission rate characteristics. So the RNA copies are things that we can actually measure, and taken from that distribution that I showed you earlier, we estimate that the emission rate will have this kind of characteristic with a mean of about 100 RNA copies per hour. The viable virion, sorry, I mean a median, is shifted to the left because there are less viable virions than there are genomic material, genomic RNA copies. Quite often you see people conflating the two in some studies, so it's very important to understand that when people are talking about genomic copies, they aren't viable viruses. We can see here that the median value is less than 1 viable virion per hour. In the example I talked about earlier, we were discussing somebody emitting 1,000 viruses per hour. That's down here on the tail. So, it is probable that of all, as a proportion of all the people who are infected, it's only a small number. Most people are going to be emitting viruses in this model at values much, much less than 1,000 viruses per hour. So if 1,000 viruses per hour gave me an inhaled dose of about 2 viruses, all these people, if you were emitting at much lower values, then the inhaled dose would also be scaled down by orders of magnitude to the point where the estimated inhalation rate is going to be so low as to not be something that would be of much of a concern, because it'd be much less than 1. Anyway, can we confirm this model's assumption with some actual data? And we can, because there's been some fantastic studies using this machine here called the G2 machine, where someone who's infected will speak or sing or just breathe into this tube, and respiratory particles are collected, and then the viral genomic material is extracted and quantified. We also had the human challenge study. So people who were inoculated and then became infected with the virus spent time in these quarantine spaces, about 50-meter cube room. And each day, an air sample was collected from within the room. And again, any genomic material was quantified. We plot the distribution of these quantified values against our model. So the model here is this blue value in terms of emission rates per hour. If we take all the values from the G2 study, you can see there's a fairly decent match with the cumulative distribution graph. What is this LOD? This is a limit of detection, and that is that the amplification process of RT-PCR has a limit to the amount of genomic material that it can reasonably amplify. And for this particular study, it was 150. It relates to 150 copies per hour. So about 60% of all of the samples from the G2 study had a value that was below the limit of detection, i.e. it recorded as 0, but it could be any number between 0 and 150. So that's what we're describing here. So it may well be that this line could have continued and followed this model or not. We don't know, because it's impossible to detect the emission rates at values less than 150 RNA copies per hour. However, if we look at a human challenge study, when we back calculate what the emission rate might be from the virus recovered from the air in those quarantine spaces, that they seem to be much greater in terms of the distribution. So, and the emission rate, see here, over 1 million copies per hour is much more common in study than it was with the G2 study. However, we can try on the human challenge study. Not only did they take air samples, but each day they took a NP swab. So we know what the ratio to genomic copies and viable viruses is on a daily basis, and we can adjust that to give an estimate of what we think the viable virion emission rate might have been for the human challenge study, and then compare it to what our model is predicting. And you can see again, it's a relatively decent fit. This isn't really a novel understanding. I think it's probably easier to see this with SARS-CoV-2 because there's so much data than we've ever had for any other pathogen. You know, thousands and thousands of people have had these swabs to see what their viral load is. But if we look at a historical perspective, we can even see it in some of the really important studies from the past. This is a study from Wells and Riley where they were looking at TB and to demonstrate that TB could be airborne and transmit from a hospital ward to a place where they were keeping some guinea pigs. But what they noticed was that 2 of our patients produced 19 out of 22 infections, even though 62 patients occupied the ward. The astounding infectivity of these 2 patients in comparison with the others was related in part of the infectivity of their sputum. And again, if we look at the Riley paper of 1978 on measles, where the Wells-Riley equation was first described, that they also note that the index case may have been exceptionally infectious. And the secondaries were about only 1/10 as infectious. So this seems to suggest that there is a very large range in infectivity and viral load of infectors and the amount of viral material that was being produced. And there are many reasons why this might be the case, and we don't fully understand them all, but this is something that I think is definitely worth further investigation. So a little bit of conclusions here. Viral emission characteristics. There's a very large range of uncertainty in viral emission rates. Massive. As I said, it's like taking a pea and comparing it to the Earth. That is a huge range of uncertainty. And there's a very large range of uncertainty then in the inhaled dose, and that will give us these orders of magnitude of uncertainty and probability of infection. It also means that, that there are certain emission rates. So if someone is emitting viruses at very, very low rates, it doesn't really matter how well or not, how well ventilated the space is, because everyone's inhaled dose is already tiny. So increasing the ventilation, it's just reducing a tiny value to a slightly more tiny value. And likewise, if someone is emitting very high numbers of viruses, maybe 10,000 or 100,000 viruses per hour, then the inhaled dose is going to be so high that your probability of infection is almost 100%. And even if you try to ventilate down, your inhaled dose remains very high, and your probability of infection remains high. So there's a limit to the emission spectra at which ventilation has a greatest effect. Okay. Another bit of uncertainty is actually, am I sharing a space with somebody who's infected? And the probability of sharing a space can be determined by kind of fairly simple number theory. But if we assume a population where 1 in 100 people are infected, and I consider a 50-person office and a 5-person office, the most probable number of infectors in that space is actually none. And then for the 50-person office, nearly 30% of them might have 1 infector. Some might have 2. A few might have 3. Very few are going to have 4 or 5. Whereas in the 5-person office, almost 95% of them are going to have an infector. So if you remember the 5-person office, if I did share it with somebody who's emitting at 1,000 viruses per hour, I would inhale a much greater dose. But actually, my probability of sharing that 5-person space with them is much lower in the 5-person space than it would be for the 50-person. I'll just show you that with a little bit of an example. Here's about 5,000 people, and I've randomly assigned whether or not they are infected. So these people, the orangey yellow squares, are people who are infected. And I'm going to assume that everybody else in the population is susceptible to whatever the pathogen is that they're exhaling. Now, if I were to take that population and slice it up into 50-person offices, like this, I can then have a look at size of the susceptible and exposed population. So these are the people in green. So these are susceptible people who happen to be in the same office as somebody who's infected, whereas these people here aren't sharing the office with anybody who's infected. So again, it doesn't really matter what the removal mechanisms are in this space, because the emission rate in these spaces is 0, whereas it's more important for those spaces. If I were to slice up that same population into 5-person offices, we can see that the proportion of susceptible and exposed now is much, much smaller. And this thought process led us to develop something that we call our proportion of people infected framework. So how does this work? So what we do is we use our model and our estimate for the viral emission rate, depending on the respiratory activity of the infectors, and we're able to create this dose curve probability of infection, which are these S curves here. So we have our 5-person office here and our 50-person office here. And you can see you need to emit a lot more virus in the 50-person office to have an equivalent probability of infection, which makes sense if you think back to the early mass balance models I was describing. In the 5-person office, the concentration is 10 times greater than it would be in the 50-person office. So therefore, you need a 10 times greater emission rate in the 50-person office. So those are what these describe, and the uncertainty here are the uncertainties in the various different removal mechanisms and in the emission characteristics in terms of the volume of respiratory particles being emitted. This curve here is the probability that an infector has a given viral load using the distribution I described earlier. So you can see if we take, say, like a 50% probability of being infected, the probability of an infector having that viral load is actually quite small. So we can multiply these two values together, and that gives us an indication of the likelihood of that event happening. And then we also multiply that then by the exposed and susceptible population, and that gives us these graphs here. So you can see we have, if you were emitting at very, very high rates of virus, the probability of being infected is 100%, because the probability of having an infector emitting at that rate is incredibly low. It means that the PPI value is also incredibly low. So we get these two curves, and what is now obvious is that this red and green curve here, which is the 5-person office, is much smaller than the blue curve, which is a 50-person office. And it's the area under these curves that represent the proportion of people infected, for if we consider a population. And by that, I mean, let's consider 1 million people either split into 5-person offices or 50-person office scenarios, and just consider what proportion then of the population is likely to be infected by this long-range transmission of the virus in aerosols. So it's maybe fairly tricky to get your head around, but this is a way that we can try and consider this vast range of emission characteristics of the virus as well as the uncertainty in the removal mechanisms. So in essence, it's a probability an infector has a given viral load times a probability that that viral load will give rise to an infection times by the exposed and susceptible population. Tested this with a Monte Carlo, and it's a fairly good fit for what we see from the Monte Carlo because it's an estimation. So this is a plot that just shows a proportion of susceptible population infected. See with the 50-person office, that PPI is much greater than it is with the 5-person office. So although from an individual perspective, if I'm sharing a 5-person office with an infector, I'm much more likely to be infected than if I was to share that same infector in a 50-person office. However, I'm much more likely to share the space in a 50-person office with that infector than I would be in a 5-person space. So this now demonstrates that the 50-person office overall has a greater riskiness compared to the 5-person space, and these are both well-ventilated offices. Can we get the risk in a 50-person office down to be the same as a 5-person office by ventilating it more? Well, theoretically we can, but the amount of ventilation air you would then have to add to this 50-person office to get to the same PPI risk as a 5-person office is unreasonably large. And this is why we can't say that there is a universal ventilation flow rate, because there are so many different factors that are pulling at each other, the different occupancy values, the different emission rate characteristics. Just going to spend the next 5-10 minutes just showing how we can apply this model to some real cases. These are some real buildings that exist, and we have some ventilation data on these, which I'm not going to show at the moment, but this is just a modelling study. So we have a nightclub, a cafe, and we compare it to our 20-person office. So this nightclub has over 880 people. It's large. If we assume a 10 litres per second person ventilation flow rate. Cafe, 90 occupants, and the exposure duration is just 2 hours in the cafe. And for the nightclub, we're going to assume 4 hours. So compare that to the office that we've described earlier, which is 8 hours. This is a similar plot that we saw before, but now the nightclub value has a different distribution of viral RNA copies per mil. And that's because when you've got over 100 people, the probability of having greater than one infector increases. And going into too much detail, that changes the distribution of viral load that you're likely to see within that space, because you're likely to be sharing it now, not with one infector or non-infector, but with multiple infectors. And so what is really driving this increase in PPI for the nightclub space is the fact that there are lots and lots of people, and therefore more likely lots and lots of infectors compared to the cafe and the office, which is so small that you can barely see them on this scale. So what would happen if we are to increase the ventilation in these case studies? What happens to the PPI? In the nightclub, you can see the PPI is quite high, and we get this rapid reduction as we increase the ventilation to about 5 litres per second per person, and on to 10 litres per second per person. Then any more ventilation has a limited effect on the PPI, such that probably it's difficult to determine this kind of thing experimentally. The office and the cafe, it's difficult to see. So I've zoomed in just on the office and the cafe. So again, you can see the similar effect, that the best reduction in PPI is seen from going from a poorly ventilated space to a reasonably ventilated space. And then any extra ventilation is not really doing a huge amount on this PPI. We can also reduce the occupancy. And by reducing the occupancy, we are reducing the proportion of people who are exposed and susceptible. Again, it's difficult to see on this scale, so I've normalised. And what you can see for the office and the cafe, where the occupancy is less than 100 people, you have this almost straight line reduction in PPI for the median values, such that if you were to halve the occupancy, you would anticipate pretty much halving the PPI. You don't see the same effect in the nightclub, because if you halve the occupancy from over 800, your occupancy is still 400, so your chance of your exposed and susceptible population is still very, very high. And it's only when you bring the occupancy of that nightclub down to almost 100 that you then see this kind of straight line effect on the reduction of PPI. So that enables us to see something that's quite interesting. And that is the effect of ventilation and occupancy differs from scenario to scenario. If we were to look at the nightclub, we can see here, if we consider it at full capacity at 5 litres per second, then our median PPI is 0.96. If we double the ventilation, our median PPI is 0.57. However, if instead of doubling our ventilation, we halve the occupancy for the nightclub, only goes from 0.96 to 0.81. And that's a community infection rate of 1 in 200. And you can see as you change the community infection rate, so the absolute values of these PPI alter because the probability of sharing it with infected obviously increases. If we compare with an office and look at the same kind of value, if we have a poorly ventilated office and it's 1 in 200, our PPI is 0.003. We double the ventilation, really doesn't make much of a difference. In fact, let's look at the 1 in 50. So, value. So our median PPI is 0.14. We double the ventilation, and the median PPI just drops slightly to 0.12. Whereas if we were to halve the occupancy of the office, it drops to 0.007. So it looks like on a scenario to scenario basis, doing some things are better for one scenario than it is for another. Another thing that's worth bearing in mind is that you can't ventilate the nightclub to rate to get the absolute value of PPI anywhere near the absolute value of PPI in an office. It's just impossible. And there are other things to consider as well when we talk about ventilating and increasing ventilation that some of these types of facilities have to consider. Cafes and nightclubs have to consider the noise that breaks out into the surrounding area because they have restrictions to the amount of noise that can come out. So there are restrictions on what these kind of facilities can actually do. There's restrictions on to things like the ownership of these spaces. Lots of cafes rent their spaces, and therefore they are limited to what they can introduce in terms of side air. But what I wanted to try and show these studies is that it's this vast range of uncertainty in the emission rate means that we have a great uncertainty in the effectiveness in reducing transmission. We can be sure that the relative risk will definitely decrease if we increase ventilation. When we start to think about what that might mean in terms of absolute figures, it starts to become muddied by the very huge range of uncertainty in the emission spectrum. So here's just some conclusions that a very large range of uncertainty in viral emission rates, and this might be true for all respiratory pathogens. Very large range of uncertainty of inhaled dose, and then orders of magnitude uncertainty in the probability of infection. Yeah, exposed and susceptible populations differ between scenarios. This all depends upon the community infection rate and the occupancy number. Ventilating underventilated spaces should be a priority, so we can see that the effect in the models is much greater than overventilating already well-ventilated spaces. Overventilating has energy and comfort penalties. and we have uncertain infection lowering benefits. Reducing occupancy can have greater infection reducing benefits in some scenarios, and we need to be aware of model assumptions and the uncertainties. Another thing to mention is that all these models are discussing and describing long-range transmission in a space. So this is the virus transmitting over distances greater than 1.5 meters or something from the infector, and that there are other routes of transmission that are likely to be important that are also very difficult to measure. So much interaction and human contact between people. It's very easy to imagine that respiratory fluids would be swapped between people. When we were discussing the respiratory particles that are emitted by infectors, the volume of aerosols is in the order of nanoliters per hour, maybe 6 or 7 nanoliters per hour. And to put that into perspective, that means you would probably have to breathe for over, or breathe in a little bit of talking, for over 85 years to generate a teaspoonful of respiratory fluid. And then if you consider the amount of time you touch your nose and your mouth and so on, how easy it would be to get a much greater volume of respiratory fluid onto your hands that you can then go and touch somebody else by accident and so on. So there are other routes of transmission that we have to be mindful of. So I'm happy to take some